Good morning. Welcome back to Unit 5 of Lean Design ENTR 3330. Today we will be talking a little bit about Toast, and then we'll spend some time talking about software and product development and product management. Here's something to think about. What is a pain point? And how do we optimize pain points to create opportunities for us to develop products on? Out with one of my favorites, toast. Toast. How many folks love toast? I absolutely love toast. Um, Toast is kind of my morning staple. Get up, throw a couple slices in the toaster, let it cook for a few minutes, lather it up with some butter, and have a cup of coffee. Oh my goodness gracious, I love it. Toast, my favorite. But how did toast come about? Well, let me just talk a little bit about the toaster timeline. The first real electric toaster, pop-up toaster, was invented back in 1919, and it received a patent and kind of sat on the shelf. We see this a lot. People invent things, they identify a problem, they invent a solution, they file for a patent, and then the patent just kind of sits in the files. By 1926, the first branded pop-up electric toaster was manufactured. It had some minor improvements to the basic design, but nobody bought it. It was expensive. It was electric. It was foreign to the consumer. People continued to make toast on their gas range as they always had. It was in 1930. The Continental Baking Company started producing something called sliced bread. They took the loaves of bread that we're so used to, and they made them more convenient by pre-slicing it and packaging it. So you could buy a loaf of bread, which in the past had just come in a little paper bag, but now the Continental Baking Company started selling bread that was actually sliced and put in a plastic sleeve. And all of a sudden, toaster sales started to grow. So the toaster was invented in 1919. It took 11 years before it really had a practical application. But it wasn't until the 1960s that toasters became a household item. And it was because the cost of them came way, way, way down. They were affordable. People understood what they were for. They were comfortable with cooking sliced bread in it. And suddenly, in the 60s and 70s, everybody in the world had a toaster. I mean, it's a commonplace item. If you walk through your house today, I'm sure you'll find a toaster. We all use toasters. But the interesting thing is, it was invented in 1919, 1920, and didn't become popular for 40 years. Not until the 1960s. And what drove its popularity was the reduced costs, so it became more affordable, therefore becoming more practical, and people were more comfortable with it. So inventions, solutions don't always happen as quickly as we'd like them to happen. There are many variables that you have to take into consideration. And remember, we're struggling against that 6-month rule of thumb for success of a product. Here's a product that actually took 40 years to be successful. I can tell you there are a number of people who tried to replicate electronic toasters, pop-up toasters over the course of those 40 years, but it wasn't until all the pieces came together in just the right fashion that they became popular. Talk about another. Let's talk about Nest. I'm sure you've heard about Nest. I'm sure some of you have Nest. I'm a little bit of a geek. I have Nest in my home. I actually have 5 of these little devices. But I started to reflect on Nest. What is Nest? Well, Nest is a thermostat. It's an electronic version of a thermostat. So if you go think back to the toaster, we've been making toast for thousands of years. People would throw a slice of bread on the hot rock or on a griddle and cook it up, and it worked just fine. The electronic toaster came on, and suddenly you could just pop the bread in, and it would be timed, and it would turn it into toast and pop it up and tell you it was ready. Well, Nest is kind of a similar paradigm. We've had thermostats for 100 years. Basic wall thermostats. You little thing, you turn the dial and the heat goes up, and you turn the dial and the heat goes down. It's a simple little controller. Relatively inexpensive. I think you can buy one of these little thermostats, the one on the right on the screen here, for as little as $4.99 at the local hardware store. And then Nest came along about 3 years ago, and they produced this really slick, glossy, electrified thermostat. And the interesting thing is, they launched the product at $249. It still sells today after 4 years at $249, versus a $5 or $9 manual thermostat. And the Nest thermostats are selling really, really well. But they do the same thing. They both turn the heat up or they turn the heat down. So what makes Nest so successful? Thermostat. This has two little wires that go to the furnace. The Nest uses the same two little wires, but it has a display. And in addition to the display, it has Wi-Fi. Now, why is that important? Why is having Wi-Fi important on your silly little thermostat? Well, it connects to the internet. So now I have a powered display that connects to the internet. What does that mean? I'm still just turning the heat on and off in the house. It's I'm not changing. The problem remains the same. The solution becomes a little bit more sophisticated. But why is that important? Well, they both control your furnace and air conditioning. Nest, however, has activity sensors. It has a wide angle view. It has a 150-degree wide angle view. It kind of knows when you're in the room. So as you walk into a room, it can actually turn the temperature up in that particular zone. It also knows, because it's connected to the internet, it knows your environmental conditions. So if it's snowing outside, Nest knows. Based on your location, it knows, hey, it's really cold and snowy. We might want to pump the heat up a little bit. It's smart. It learns from your behavior. So if you turn the heat up every morning at 7 o'clock, after 7 to 10 days, it'll start doing it for you. You don't have to do it anymore. And if you turn it down at 9 o'clock when you leave the house, okay, and you do that every day for 7 to 10 days, well, it'll start turning it down every day at 9 o'clock. Doesn't it, in fact, have a variety of sensors? And since I had to set up an account, sensors, moisture knows a little bit about me. It's a pretty sophisticated device. Now, it still is just turning. It also knows when I come and go. It has sensors that know but when it's I'm in actually making it more. That's pretty cool. Very much more. It's also pretty creepy. Another thing that knows who I am, where I live. It knows when I come and go. The internet, you can actually set your temperature before you get home. It can also extrapolate my spending habits during the day, and you're out traveling. I'm a cheap person, and you keep the heat down all the time. The furnace up high, or cheap or frugal, when you left the house. Or if I'm you can do it on the road. You can adjust your thermostat. I have 5 zones. I can heat up all the zones throughout the house. It knows when I'm on vacation. I can check on them, make sure the temperatures are comfortable all day long. I can manipulate them if I need. If I have somebody coming over and has access to my phone, they like a really through the app room. I'll turn the zone up. So it's pretty cool. And the other thing is because it's connected to the internet, it also because I have to put in something called auto telephone number. Over the I don't have a landline anymore. OTA, it knows my mobile phone updates, which means that now I'm sharing the parent company of Nest can update the software. Well, how did they do this? How did they do this, and why did they do this? Well, Google did this because people complain about the thermostats, right? I'm not sure about that. My thermostat was always pretty cool. It was pretty simple. Turn it up, heat goes up. Turn it down, heat goes down. Why would Google want to have Wi-Fi access to my thermostat? Well, they talked to customers, and customers said, well, it'd be kind of neat if you could do it automatically, if it could learn, if it could get smart, if it could do things for me. So that's a good thing. So Google went and they developed their product specifications, design manufacturing specifications based on the technical requirements of the user. You know, when they come and go, turn the heat up, turn the heat down, manage the environmental conditions. Those are technical specifications. On the usability side, the usability specification, they made it look really pretty. Turns out the folks who started Nest came from Apple, so they gave it an Apple-esque kind of round, smooth look with a fancy interface. They made it really easy to use, really easy to set up. So the usability specifications were based on a little bit on Apple design, but very much so on ease of use by consumers. They want to keep it as simple as the original device. The downside to all of this is I've now allowed Google to enter into my home. Google doesn't care about turning up my temperature. They don't care about turning down my temperature. They don't care about automating my temperature. Google wants to know about me. They want to learn my habits. And this is just another access point for Google to learn more about me. It solves a problem, but it opens up a huge opportunity for the parent company of Google, of Nest, which is Google. Let's talk a little bit about software and product development, and this is going to be really familiar to most of you. You're fairly technical folks, particularly CIS folks in the classroom, but I need to go through it because I think it's really important that we're aware of the different types of software, the different applications of software as tools in product development and, more importantly, product management. Why do I care about software development? Look at some of the bugs. As excited as you are about the iPhone, how many updates do they have to do on a regular basis? How often does your PC have to update because there's a hole or a wormhole or a bug in it? Look at Toyota with the airbags. How much analysis was done? How much work was done? We're talking about lives. We're talking about if my phone doesn't work and I really need it because there's a bug in it and I'm on a ship drifting in the ocean and I want to make a phone call and it doesn't work, it's a problem. If my airbag misfires or doesn't fire, it is a problem. Software is huge. One of the most famous bugs in software, and this goes way back, but it's a really important one. Back in 1996, there was a test flight of a rocket, and it blew up within just less than a minute after launch. It was the Ariane 5 rocket, and it was a much touted rocket. It was supposed to be the coolest thing in the world. Very sophisticated, all software driven, no human intervention. In the course of the software development to run that rocket, one little engineer slipped a digit, and he did an incorrect conversion with one of the integer values, and the rocket crashed. Everything else on the rocket was perfect except for one little digit. And that, if you look up the Ariane 5 rocket, you'll see how important software is in pretty much everything we do today. Everything we run, even the Nest thermostat runs on software. So it's critical that you have really good and tight software. Not only is it a functional importance, but it's also in certain situations it could involve it could be life-threatening. So we have to be really sensitive to it. So that's the incorporation of the software, but also in the process and the development of our products, how well we use the software to develop those products is critical. And what type of software we use, and the processes that we use, the software process. It's kind of tough because this isn't a video, but has anybody, I'm not sure, I guess I just asked you to reflect, how often have you had a bug on your computer and you had to reinstall the software? Or have you been writing code and you found that you missed a digit and the whole program crashed? How about this is iPod, but how about your iPad? When's the last time it froze? or you ever try to start your car? If you have a newer car, and there's a short circuit, there's a problem with the software, and the engine won't fire. I mean, these little things, these annoyances, and they're software related, and sometimes really really simple problems. I reflect on the Mars rover. The Mars rover started. It's been running for years, and then suddenly stopped running, and they had to send new code to it because apparently when the original code was burnt onto the ROM on the rover, it had a expected life span, and which was very short. And at the end of that lifespan, the software was meant to shut down. It turns out the rover outlived the time, the amount of time provided in the software. It was still functioning, but because of this little one line of code in the program, it just shut down a mechanically sound device. So they had to re-upload, re-flash the memory in the device to get it running again. So software is critical. It's critical in the development, and it's critical in the operation of our product. Software is used was originally created to solve problems. Software is not a single person. It's like we like to say that we got a software guy in a cage or a software guy in a cube that's writing the code. It really involves a ton of people. It involves the code person. It involves engineers. It involves strategy people. It involves marketing people. It involves product development people. To solve a problem, you really need to analyze, understand what the problem is, and then synthesize with all of these other parties to make sure that you understand what you're trying to do, how you're trying to do it, and the implications of your software, your code on other parts of the program. This is from McCall's quality model. It's a Air Force. It's actually used in the Air Force. And this is just an example of the complexity of software in the QA analysis of software. How correct is it? How does it run? How reliable? How efficient? What's the integrity? Is it easy? Can you maintain it? Can you update it? Do you have access to be able to test it? Is it flexible? Can it be used on other things? Is it portable? Can you reuse it? I mean, there's tons of considerations that have to be made, and then you have to be able to test all of them. You have to make sure it's reliable and consistently reliable. You have to make sure people can use it and understand it. I can't tell you how many times I take a product out of a box and the instructions for the software are just mind-boggling. I'm an average consumer. This should be really easy to use. The underlying engine can be as complex as you want, but the user interface, usability has to be right for the customer. So this is a good example of the complexity of designing software and, in fact, testing it. Typical software development team has an analyst, a designer, a program tester, and a trainer. And this oversimplifies it. Typically, we'll have teams of analysts, teams of designers, teams of code people, teams of testers. I'm working with a project right now. It's a integrated device that has a software application on it. We need to test the usability, just the usability, not reliability, not functionality, just the usability of the app for this product. And it's going to take us 3 months with about 12 people testing it and debugging it. So it's pretty complex. It usually involves a number of people on a team supporting it and collaborating. Back to our product development process, remember we talked about the 5 steps: strategy, ideation, concept, build, and then rollout. Software is involved in all of it. In the definition of agile product development, it becomes even more and more critical at each step of the process. It's what helps us condense the schedule. It also helps us increase our efficiencies and optimize our product. Important things to keep in mind. Make sure you stay focused on the problem, understand it. and then synthesize a solution. It's kind of the ideation exercises we've been doing. You also have to understand that as you're developing the product, either the customer or the team requirements may change. So you need to have built-in flexibility. It's always good to have different perspectives. That's why we have multiple people testing software and product development. You should stick with the basic engineering concepts. This is why it's always good to have a software or computer science person on the team. There are some basic principles that should be used, flow designs and coding protocols that should be used. And then make sure you understand and appreciate the power of the tools that you're using. Don't overextend a software product or an application in a product development rather than use a more appropriate one. So you want to make sure that you keep your system boundary, the operational elements of the software in mind. It can only do what it's designed to do. If you try to overextend it, it's going to break. There are a number of different models of design. This happens to be the waterfall model. I'd call it a serial model. You do one thing and then the next thing will happen. Once you finish the next thing, you go on to the next. You start with the requirements, you go into design, system design, then program design, then you start writing the code. Integration testing, your first round of testing, then you go into the system testing, and then usability and acceptance testing, and then the final stages of operation and maintenance. I mean, it's called waterfall because it kind of flows in a linear fashion. It's presented here as a waterfall. The V model, and again, you could make this linear, but the V model, it just looks like a V. You start with your requirements, you get into design, and as you start to do your design, you do some basic testing, so it's somewhat in parallel. Then you go into your program design, and then you make it at the same time you're integrating, you're testing the integration of it. When all of that's done, you do your coding, and then you kind of work back up to make sure things work the way they're supposed to work, or you correct and then you go down again. It's called the V model. Prototyping. This is probably more relevant today. You start with a concept and then you do a quick prototype, and then you modify it, adjust to go back, prototype again, and you continuously prototype and try as you go. I actually like this one the best because we can kind of get a feel for what we're doing. We can see what it's looking like, see how it's coming together, and we can pivot, we can change, we can modify, and then rerun it again. This is called a prototyping model. The operational model, where it's just you build it and you design it, build it, and test it. Transformational model allows you one opportunity to make modifications to optimize the original specification, and then you test it. Not a lot of flexibility. It's a linear process. Phase model is really kind of it's also called stage gate model. You build, you release, you test, you build a second release. They're running in parallel, so the development people are working on it while the production people are testing it. There is some input in the design, but it's similar to the prototype model. It allows for the users to actually see the product and try the product as it's being developed. So you start with the very early stage. I get to check it. While I'm checking it, you're going on to the next stage, and then I check the second stage. You're working on the third stage, and then I get to check the third stage. I can give you feedback, but by the time I give you the feedback, unlike the prototype model, you're already building the next stage. So there are some modifications that can be made, but not a lot. It's a pretty efficient system. It's a pretty focused system. Does not have a lot of flexibility. Spiral model is a kind of crazy one. This is kind of like everybody's working on everything at the same time. You start with your goals, You start small and you kind of work out. You have a core team. You start with the project, a small group of people, and then you start to develop it, and then you constantly modify it as you're going. And the more modifications, the more implications, the larger the team, the larger the product, the project becomes. The spiral model is, I also like to call it the accidental model. It kind of grows with the program. My concern with this type of model, and frankly happens a lot, is you lose control. You just have too many people involved. There are too many opportunities for it to break. Sometimes it gets diluted. I had a project, a toy car project, where we just kept adding stuff. People are adding stuff left and right, and from the coding people, from the designers, they'll tell you whenever you use this type of model, yeah, you can build a really cool product that covers pretty much everything for everybody. But each time you tweak one little piece, it affects the whole model. So in the spiral model, you can get a really comprehensive, really robust program or product, but you also become incredibly vulnerable. The reality of how it works, to be honest with you, no matter which process you use, it's just kind of a crazy free-for-all. The project manager really has to kind of control it. You start with the requirements, you try to lay out the design, you try to build it, and then you try to deliver it. And over the course of that project, a whole bunch of stuff's going to happen. No matter what you think, and no matter how strict you try to be, there are going to be points where you realize that, hey, we missed a feature, or this feature doesn't exactly do what I expected it to do. Maybe you need to rethink it. So the reality of it is, you need software, you need to control it, you need some kind of process, but in the end, it's going to be a bit of a free-for-all. You can't live without it, and you can't live with it. So the best advice I can give you is use it wisely, and have a point person managing it. In the case of the project for this class, the person directing the program for any software development should be the project manager. Agile development, emphasis on flexibility. As I mentioned, you know things are going to need to change. You want to do it quickly and capably, efficiently, but with flexibility. You need to take people, the input of your team and of your customers over the process and tools. So if you start with a linear program and you realize that it needs to be a spiral or a prototyping model, then you should change to it. You should invest time in producing really good software, and focus more on software that works well than on the documentation, and try to explain to people how to use the software. Customer collaboration is key, and you need to be cognizant of change. It's going to happen, and you should be in a position as an agile project manager. You should be in a position to react or respond to changes quickly, rather than dropping back and having to figure out what are you going to do. Okay, where's my plan B? You should always have the plan B in your pocket, anticipating change. I go back to a good tool we talked about it last week, a couple sessions ago. Gantt charts, very, very important for project management, particularly in software, to keep the system tight and focused on what the end goal is, and to allow the ability to add extraordinary events, things that may occur in the course of the development of the project or the software. So you're cognizant and you're tracking them, and you're aware that they've been added or subtracted. Gantt charts or action plans are really, really important to project management. Here's my top 10 list of issues or risks in software development. You might not have enough people, the schedule may be crazy. The schedules will always be crazy, and you will never have enough money. If you are too close to the coding, and don't talk to your customers, you may end up with the wrong functions or the features and functionality of the product. It may not do what it's supposed to do, and people are not going to be happy that they have a product that doesn't work. User interfaces are critical, or you can read the rest. A lot of timing issues. If you don't have a good program management plan for software, a lot of really, really, really risky timing issues. The upside of a good project management program using software, and to put a plan together, an effective plan, is you should have a clear scope. You should have a clear deliverable and schedule. People should know who's doing what, who's responsible for what, and that again goes back to the Gantt chart. Really helps identify who's supposed to be doing what the deliverable is, and when it's supposed to be delivered. Standards and procedures are critical. You should have a test plan that's clear. Training plan, that's on the back end of the curve as you start to roll the product out. Security plan, really, really important in software. You need to be cognizant of what the risks, what the holes are in your software, what the potential vulnerabilities of the software are, and you should have some kind of risk management plan. And then you should have a back-end maintenance plan. How are you going to do updates? We talked about Nest. Nest does over-the-air updates. You can get regular updates. I'm unaware when they do updates. You should have a maintenance plan in place to constantly update your software. The hardest thing to do when you're using software, actually when you're doing a product development, is getting the specifications or the requirements. This has to be really tightly controlled with a really clear focus on what the deliverable is. It starts with a collection of input from everybody. You homogenize that, you analyze what the inputs are, you want to make sure you understand what the software, what the product is supposed to do. Once you've analyzed that, once you've collected the input and you've synthesized it, you've analyzed it, then you want to write up the specifications and circulate the specifications. You want everybody to buy in. This is what it's going to do. This is how it's going to do it, and this is what it's going to look like. And then, so you circulate that documentation. You make sure everybody buys into it. And then you have a final document that's called an SRS, or a software requirement specifications. Similar to our RFQ, it clearly defines what the software is supposed to do, how it's supposed to work, and what it's supposed to look like. The SRS is critical anytime we have a software element to a program. The other thing that's really, 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 really important, and I think at some point in this course we'll talk about my little RC car, is testing. We do research. We talk to our customer. We'll talk to our customer in this class at least 3 times. Hopefully over 100 people will be exposed to our product, and we'll collect their feedback. But we also have to do testing, literal hands-on testing. We should test this product from the very earliest stage. As soon as we get a prototype, we should be testing it. We should be testing it to make sure it works, that it does what it's supposed to do, it looks the way it's supposed to look, and that consumers will accept our solution to the problem. This is true for software. This testing slide can be applied for almost every element in our program. In software, we start with the product. We first test to make sure our software works in the product. It's clearly integrated in the product. It meets the design specifications. Second thing we want to test is to make sure that it does what it's supposed to do functionally. It gives you the desired output. We then want to check to see if it performs the way we expect it to perform. How many steps? This is always a test that we use. How many steps to get to the solution? Do you have to have 12 buttons to turn the TV on? Or if you hit one button, does the TV come on, your surround sound comes on, and the lights go down? So what is the performance? Does it meet the customer's requirements? Does it meet the demand of the end consumer. Will it do what they want it to do? And then we do some installation tests. We actually want to take the software and we want to send it out to actual testers, users, and have them test it. So there's a ton of testing that should take place. You don't test the product at the end. You test the product at the beginning and all the way through. Just a few definitions. You guys probably already know these, but I just throw them out there. Cloud computing, we all use it. Open source means anybody can add or modify the software. Apple uses closed solutions. Google and Android are open. There's a big debate on which is better. I actually prefer open solutions because that's where we can draw in some of the best of minds. Open solutions are also vulnerable, can be hacked really easy. Platform, API. API is might be a new one. Platform is just kind of generic functionality, and it's kind of similar to the cloud. It is the infrastructure on which your software is going to operate. An API is kind of the toolkit. It's what it's the hooks and the drivers that make the software run and talk to other software. SAS, software on demand. It's just it's available. I mean, with the advent of the internet, everybody can have software. It's typically run within a system, but it's generally available to everybody, particularly within a local network. And then we're talking Web 2.0 here. We're actually talking about Web 3.0. It's just next generation of Web 3.0. It talks a lot about IoT, Internet of Things, connectability. But just some basic terms you should be familiar with. That's it for today. Have a great week, and I'll see you next time.